Hello, today we'll be proposing our project of an autonomous UTEP mass transportation system. Our team consists of Ricardo Alvarez, Luis Medina, Jason Jabalie, myself, Jessica Coria, Elizabeth Artalejo, and Aaron Flores. Our autonomous mass transportation system is meant to help UTEP provide a cost-efficient way to help students arrive at their respective destinations in a timely manner. This system will be more convenient to students as opposed to traditional route stops. Our solution is an autonomous vehicle capable of supporting 15 to 20 passengers that can follow a designated route while being aware of its surroundings, in order to minimize problems that may occur while maximizing the speed of the vehicle. This system intends to be more efficient when transporting students throughout the UTEP campus using a magnetic railway. Shuttle stops will account with signaling features which will allow shuttles to know if they need to pick up a group of students or keep driving through its intended route. The shuttle will also be equipped with motion sensors, which will allow the shuttle to register surrounding information in real time and act accordingly. The AI in the shuttles will be able to read changing weather conditions and act in the most efficient manner. The shuttles will also be equipped with solar panels to power amenities, which will be part of the shuttle to accommodate students. The system will have to undergo several tests and audits by the City of El Paso so that it is approved and able to operate. Our team will work closely with TechStot so that the system is following state and city guidelines correctly. Our team will also perform weekly inspections at first, then switch to monthly inspections to ensure that the system satisfies the requirements they have in place. Throughout this presentation, the key terms that will be used are as followed. In this table, you will see to your left the acronyms and to the right their definitions. AI is Artificial Intelligence, UTEP, the University of Texas at El Paso, TxDOT, Texas Department of Transportation, VNV, Verification and Validation, RVM, Requirement Verification Matrix, CBA, Cost Benefit Analysis, CONOPS, Concept of Operations, GPS, Global Positioning System, and lastly, RBTM, Requirement Bidirectional Traceability Matrix. Within our organization and management section of our system, we have decided to assign roles to each of our team members. Ricardo Alvarez will be our team leader, Jason Jabalie, our customer interface manager, myself, Jessica Coria, our design manager, Luis Medina, planning manager, and Aaron Flores and Elizabeth Artalejo will be our quality managers. In this project, we'll be following an agile system lifecycle model that will be expanded over a 5-year lifetime. By following this type of lifecycle model, we are able to continuously improve our system throughout its lifecycle. On the left, we have the activities that we have done so far within 5 different phases, those phases being requirement, design, implementation, testing, deploy, and lastly, review. On the right of the slide is our Gantt chart. This displays the timeline for actually building our system, from the conceptual design of our AI to getting final approval from the City of El Paso and UTEP. For our risk management, we have created a probability and impact matrix, also known as risk matrix. Together, these parameters can be quantified on a scale of 1 to 5 to be used in numerical analysis. This table shows an example of that quantification. The values for each risk probability and impact can be multiplied to obtain an exposition factor, ranging from 1 to 25. The exposition factor is used in all risk management efforts as shown in this table. An example for this mitigation activities for our project would include an exposition factor less than or equal to 11, where risk will be accepted and no mitigation will be performed. An exposition factor greater than 11, mitigation activities are planned and enacted. An exposition factor equal or greater than 20, contingency plans are created and the mitigation activities continue. In continuation from our risk matrix, we have created a risk table. In this table, we identified all the possible risks that can affect the operation of our system. Highlighted, you will see 3 colors, green, yellow, and red. These are just examples we will be talking about that go over each of our risk options to accept, mitigate and create a contingency plan. To the right, we will start with the green highlighted risk. This risk is the system's batteries/solar panels malfunction due to overheating or discharge. We gave this risk a probability of 1 and an impact of 3, giving us a factor of 3. Due to this being less than 11, we choose to accept this risk just because it will not harm the operation of our system. Next, we will talk about the second risk to the left. It will be highlighted in yellow. The system's magnetic railway does not function properly. We gave this a probability of 3, an impact of 5, which gave us a factor of 15. Due to this being greater than 11 but less than 20, we will choose to mitigate this risk, which means just monitor it and do anything possible that will not let it continue to harm the operation of our system. Towards the bottom end of the left chart, you will see the risk that is highlighted in red. The risk that says the system hits a jaywalking pedestrian. We gave this a probability of 5, an impact of 5, which leads to a factor of 25. Due to it being above 20, we will have to mitigate and create a contingency plan for this risk. This is a high risk just because it is something that could stop the use of our shuttle system and potentially cause harm to anyone that is around the use of our system. In order to achieve the goals of our shuttle system, we propose that integrating artificial intelligence and autonomy into the shuttle system will help lower the cost of maintenance and lower the time it takes to transport students and faculty around UTEP's campus. This will result in a shuttle system that is economically beneficial to UTEP. The AI system will take in a variety of different sources of input such as motion sensors, temperature sensors, GPS coordinates, image recognition software, and a cell phone application to ensure proper navigation of the shuttle route, proper shuttle start and stop procedures, as well as compliance with emergency vehicles. The purpose of this project is to improve the means of transportation for the students and faculty around campus. As mentioned previously, the system will operate through a magnetic pre-selected route in the UTEP area. The students will essentially signal the shuttles in designated pickup areas, reducing the wait times. The system will operate using AI technology that our tech team will monitor closely and ensure is working at optimum level. We will be working closely with TxDOT to ensure that we are following city regulations implemented by the City of El Paso. The following is an example of a use case model that describes the goals of the different users, the interactions between the users and the system, and the required behavior of the system in satisfying these goals. In the described use case model, we can observe that the students will have the availability to use the application to request a shuttle stop at a designated location and then board the shuttle. The server will host the application that the students will use to request stops. It will designate a stop and store logs and services. The IT support for the shuttle will have access to these logs and services to update and maintain the shuttle and the AI system. IT can also access manual mode in the shuttle for maintenance purposes. The AI system will be able to traverse the designated route, make the designated stop assigned by the server, and generate logs of every sensor and movement for the IT support to use for reference. In order to define our system, we came up with 20 requirements. Each requirement is assigned a unique requirement number and a traceability ID number. Requirements were then categorized as 6 system requirements that support overall operation, 5 software requirements, 4 hardware requirements, and 5 safety requirements. These requirements help to ensure stakeholder satisfaction and proper planning and design of the system. The System Requirement Review is a tool that helps us note our previously mentioned critical requirements and allows us to show the verification analysis on them. This tool helps us determine if the requirements are clear, consistent, complete, singular, necessary, feasible, and verifiable. From this tool, we can refine or change requirements to better suit our project. The Requirement Verification Matrix is a document used to determine how each unique requirement will be verified. It lists the unique requirements number, the requirement traceability number, the requirement, and which stage of the project that the verification will occur for each requirement, and at which level the verification process will take place. The numbers in the verification section of the document represent the testing technique that will be performed. For example, Requirement 1 states that the system shall have the capacity to transport 15 to 20 students per shuttle. This was the first requirement, so it was assigned a traceability ID of 1.1. For this requirement, we determined that verification must take place in the design and qualification stages. Within the design phase, we decided that the best verification method would be to use a walkthrough inspection, since the seats available are going to be apparent and the capacity is observable. For the qualification stage, we decided that a checklist would be the most efficient verification method. This is due to the fact that we can easily observe and verify this requirement with a simple analysis technique. We determined this verification testing will occur at the systems level because we will need all assembled components and subsystems in order to successfully test.
Hello, my name is Jason Jabalie, and I will be presenting the design phase for our project. In the design phase, the design team will create plans on how the system railway will be built and determine the route it will take. Officials from the City of El Paso and TxDOT officials will be consulted throughout this phase to ensure that our designs are meeting any regulations and also identify any certifications and accreditations that we will need for our system to meet. Continuing on, the team will perform certain IVV activities for our project. This will include a failure mode effect analysis, a cost-benefit analysis, and a requirement bidirectional traceability matrix. Next, I will be talking about the failure mode effect analysis, or FMEA, which is a bottom-up procedure for the analysis of potential failure modes within a system or process. It then helps determine how to eliminate such problems. The FMEA is widely used in various phases of a life cycle, but is heavily used in the design and manufacturing phases. There are 4 types of FMEAs: design, functional, system, and process, but we will be focusing on the design FMEA for our project. As we can see from the chart, this is how an FMEA works. The system is reviewed, and then we assess what can go wrong, and then we determine what the severity of the negative effects are and the likelihood of them to be detected. This will help us to identify any problems that can happen and to also help minimize the impact of these said failure modes. Here we have our FMEA. The first column is our failure modes, which consist of a magnetic railway failure, an autonomous shuttle failure, an AI failure, and a communication network failure. Our second column is the severity of effects, which is how severe the effects will be if a failure does occur. Our third column is the likelihood of detection, which is the likelihood of a failure actually being detected. Both of these 2 past columns are ranked on a 1 to 10 scale, 1 being the lowest and 10 being the highest. Using the AI failure as an example, the severity was given a 10 because it would be detrimental if the AI system were to fail for our system. The likelihood was given a 2 because it is very hard to detect a failure. The cause could be that there was a bug in our AI system causing a malfunction. The chosen mitigation strategy was the shuttle tech support is in charge of running a test every morning to ensure that the AI is reading data efficiently. In this slide, we have our cost-benefit analysis, or CBA. The purpose of the cost-benefit analysis is to identify the most critical risks of the projects so that we can focus on them with the proper testing and also see how much it would cost if the risks were to happen. The first column is identifying what risks there are. The second column and the third column are the probability of failure rating and the severity rating. Both are ranked on a 1 to 10 scale, 1 being the lowest and 10 being the highest. The next column is the total factor. That is a factor of multiplying the probability of failure rating and the severity rating together. The next column is the VVT cost, which is the cost of performing the test to identify integrity of the life of a product. Next, we have the appraisal cost, which is the cost of rework based on the probability of finding faults in the system after performing the tests. Next, we have our impact cost, which is the cost of the impact caused by not testing. Then we have our total cost, which is all the costs that have been added together. To further explain the cost-benefit analysis, we will be using an example of the system hits a jaywalker pedestrian. This risk is very important since it can result in a loss of human life. Since we are taught to look both ways before we cross the street, we can assign the probability of this happening at 3 just because it's not every day that somebody gets hit by a car, but it does happen. Severity is given at 10 because, as we stated, it can cause a loss of human life. Multiplying these two numbers together, we got our total, which was 30. This was one of our highest ranking risks for our project. We figured that $158,000 should be enough to mitigate this risk. The majority of this money, $150,000, would be set aside due to any legal fees that may happen due to any failures. Continuing on, we have the System Requirement Bidirectional Traceability Matrix, or the RBTM. The main purpose of the RBTM is to determine whether or not all of our system requirements have been addressed and that they can be traced to an element of our system. We began by listing all 20 of our system requirements horizontally. We also listed 14 elements of our systems vertically, which can include things like our power system all the way down to our maintenance team. There are two types of traceabilities in this matrix. Forward traceability, which is the requirement to an element, and backward traceability, which is an element to a requirement. The forward traceability is indicated by a star. Backward traceability is indicated by a slash. If either a requirement or an element does not have a forward or backward traceability, it is not needed in our system and will be removed. Taking an example from our system's RBTM, we can look at requirement 1. This states that the shuttle must have the capacity to transport between 15 and 20 students. As we can see, there is forward traceability indicated by the star on component 2, which is the hull of the shuttle bus. This makes sense because the hull of the shuttle bus will satisfy the requirement and will hold 15 to 20 students. Continuing on, we can see that component 2 has backward traceability to requirement 1. This also makes sense because without the shuttle hull, there would be no way to transport 15 to 20 students. Implementation phase. In the implementation phase, IVV practices are implemented to document designs, contract external stakeholders, build and purchase elements of the system, and test the elements to ensure verification of requirements. The purpose of this phase is to rid the system of errors and unnecessary elements. This phase utilizes the subsystem components test document as well as the acceptance test document to complete the following IVV activities: the plan testing process for elements and components, define a structure and management plan to perform testing, define test cases, document test date, obtain customer and stakeholder acceptance test. Component interface analysis. This is our component interface analysis for our project. First, it would be hardware to hardware, which would include the shuttle to railway system. Second would be hardware to software, which would be power system to AI. Third, it would be software to software, which would mean it would be communication system to sensor system. And last, it would be human to system, which would be human to AI. Component test document. Image recognition. The integration test procedure for this is as follows. The AI will be done by the shuttle tech team composed of computer scientists and software engineers.
Once that software is up to the City of El Paso standards, which will be determined by both the City of El Paso officials and TxDOT, we will begin the virtual simulation to test out the AI. We will place image recognition cameras that will capture data for the AI. Once the AI alongside the image recognition cameras perform at optimum standards, we will begin Phase 2, which is the real-life environment testing. Phase 2 will be composed of a control environment, which will be a small area big enough to test the shuttle and AI. There will be numerous image recognition cameras placed throughout the shuttle. In Phase 2, the image recognition cameras will be tested on how efficient they are at recording crucial information such as recognizing obstacles, for example, pedestrians, traffic signs, student signaling to stop, etc. Once the image recognition meets the City of El Paso standards as well as the intended project standards, the final phase will initiate. The final phase of the project will implement the image recognition cameras throughout the selected route as well as the shuttle. Communication and feedback. Integration test procedure. Communication and feedback will first be tested under a simulated environment. Once results meet the desired parameters, Phase 2 will be initiated. During Phase 2, these two parameters will be measured in a real-life environment to ensure they meet the specifications given by the City of El Paso. Sensors. Integration test procedure. Motion weather sensors will be first tested on the virtual simulation where they will gather data for the AI. Once they have been approved by the project manager, we will move on to Phase 2. In Phase 2, various motion weather sensors will be placed in the designated control environment and will be tested on how effective they are at gathering their intended data. Once the data gathered by the sensors meets the parameters given by the City of El Paso, the last phase of the project will start. The final part of the project will be placing all sensors around the selected route. Validation criteria for acceptance. Image recognition. Overall assessment. The image recognition subsystem was graded on a pass-fail grading scale. The subsystem has passed the test by successfully completing the following criteria. The image recognition system detects 1,000 images and categorizes them with 100% accuracy. During assessment, the subsystem was capable of detecting and categorizing 95% of the images that were provided to it. Therefore, the subsystem was considered accurate enough to have passed the test. Communication and feedback. Overall assessment. The communication and feedback subsystem was graded on a pass-fail grading scale. This subsystem has passed the test by successfully completing the following processes. At all time, the shuttle must successfully upload its GPS coordinates to the system server. The cell phone application will download the coordinates from the server and display real-time location. The cell phone will upload signal to server via application. The shuttle will download the cell phone signal from the server. Sensor. Overall assessment. This assessment consists of two separate sensor tests. The motion sensor subsystem was graded on a pass-fail grading scale. This subsystem passes the test by successfully meeting the following benchmark. The sensor detects the correct distance from an object and tracks it through time with 100% accuracy. The weather sensor subsystem was graded on a pass-fail grading scale. This subsystem passes the test by successfully completing the following benchmark. The sensor identifies different weather conditions. Using separate measuring devices, we measure the current temperature at the start of the test. If the sensor is able to identify the same temperature 80% of the time, it will be given a passing grade. If both subsystems receive a passing grade, the overall assessment of this system passes. Retest plan. In case of a failure on a test, a 3-step process will be followed. The first step will be to understand what went wrong on the system that made it fail the test. The second step will be to fix any issues that the test revealed. Finally, the third step will be to schedule a new test to check whether the issue was resolved and the component can pass the test.
The integration phase will be conducted in 3 stages. Stage 1 is the AI system. Stage 2 focuses on the shuttle. Stage 3 focuses on the hardware and software system. To elaborate on Stage 1, the phone application must be fully integrated so all components of software are fully integrated with each other. Elaborating on Stage 2, the shuttle system and the railway system must be fully integrated with each other. Elaborating on Stage 3, integration of hardware such as sensors will be integrated with image recognition software. built-in test BIT system. To improve our system through the integration, we will incorporate a built-in test system into our project. The built-in test system was planned for the shuttle performance evaluation system, which will include tests for things such as image recognition, weather sensor, motion sensor, AI decision-making algorithm, mechanical shuttle components, and communication server data transfer. By having this built-in test system, we will be able to ensure that our system is fully integrated and will allow us to identify any problems that could occur within our system. For the built-in test strategy, we have built-in test entry criteria, testing strategy, testing sequence, and testing exit criteria. An example of the built-in test entry criteria is all sensors are fully functional. For the criteria is that sensors are recording intended data effectively and sensors have no damage. The testing strategy is the overall logistical approach for the shuttle system. Diagnostic test information is uploaded into a database and then is reviewed by involved engineers of the project to perform capability studies. The testing sequence highlights specific testing parameters that each test is performing for. For example, there is a test to confirm if any mechanical issues are present, or another example is there is a test to confirm if the shuttle is sending data to the server. The testing exit criteria is the verification that all requirements of the built-in test strategy are met. Examples include verifying that all tests have been performed and reported, or another example is verify predetermined solutions to testing errors that have been executed. Risk and cost analysis for integration test. When evaluating our integration test, we referenced our cost-benefit analysis to identify a testing methodology and a high risk to our project. We identified that the safety aspect related to the sensor connectivity of the artificial intelligence system would be the largest risk. This slide illustrates an integration test that will gather data to determine the integration functionality. For the artificial intelligence and sensor connectivity, certain parameters were addressed, such as the hardware, software, and other preparations, requirements addressed, prerequisite conditions, integration test input, expected integration test results, criteria for evaluating results, integration test procedures, assumptions and constraints. In the hardware, software, and other preparations, the hardware is the sensors that detect the weather and the motion that will be placed throughout the entire area of the bus. The software is the AI that is gathering the data that is recorded by the hardware, which is the sensors, and is prepared by the computers at the Shuttle Tech Support Center. The requirements addressed are such as the AI system being able to adapt to different types of weather conditions, and the system having the ability to have image recognition software to categorize these images recorded by the AI system, and the system itself being able to provide feedback to the Shuttle Tech Support Monitoring AI. There are certain prerequisite conditions such as the sensors showing no visible sign of damage, the AI system being up to date, and the Shuttle Tech Support System ensuring the AI and sensor interface. Qualification and acceptance. For our project, we will have our system go through a qualification and acceptance phase, which will help ensure that our system meets system-level specification and result in customer acceptance. The qualification and acceptance document consists of the tests that address each of the system-level requirements for the artificial intelligence mass transportation system. For the qualification acceptance strategy, there is a qualification acceptance entry criteria, the testing strategy, testing sequence, and testing exit criteria. For the qualification acceptance entry criteria, the subcomponents must have been tested and have been submerged to generate the system as a whole. For the testing strategy, different scenarios will present a pass-fail score of each requirement of the system. Testing sequence is based on the testing of the order presented and is also based off the testing exit criteria off of a pass or fail criteria. Stakeholders will provide the certification, and those stakeholders being TxDOT and UTEP. Multiple tests were performed, but for the sake of this presentation, we will focus on test number 1, which is a maximum capacity test that is performed to determine if the shuttle buses are able to meet the minimum requirement. Up to 20 volunteers will be involved in this test, ranging in size and weight, which will total up to 3,000 pounds. They will be placed in the shuttle to determine if it has the capacity to accommodate 20 individuals. With all 20 passengers on board, the shuttle will drive the course and this data will be gathered, and then given a determining pass-fail rating. Occupancy, capacity, and velocity data will be recorded in order to evaluate if the shuttle is able to reach minimum street speed limits with varying capacities of 0 to 20 people.
7.6 Maintainability. For the subsystem of the magnetic railway will be monitored and upkeep in a daily basis to ensure that the best quality of transportation possible to our customers is provided. Any mandatory replacements will be done every 3 months in order to ensure that the best quality of systems, regardless of whether it shows damage or not. The shuttle bus itself will be tested on a daily basis to ensure that there are no damage or signs of damage that can be caused by accidents in the future. If there is a damage that goes unnoticed by the professionals in charge, the AI will report with daily diagnostics reports, which will be assessed by the shuttle tech support. The AI, since our project is heavily dependent on AI, the AI will be required to provide daily checks on itself and on the rest of the system. This will help maintain the AI and see if we can figure out if there are any bugs or updates that need to be done to the AI system. For the sensors and cameras, they will be monitored daily to ensure that they are working effectively to capture the data needed for the AI, and the sensor will be changed every 3 months in order to ensure that the best quality the system can offer. Availability. During the lifetime of this project, more shuttles will be added to the fleet in order to provide the necessary efficiency of use to the students. This will be done as needed. More storage capacity will be added to the server as logs become data and used only for reference. This will be done in order to maintain high demand of application instances that the students will download to their phones. As UTEP grows in both student population and buildings, the university will need new routes for the students to utilize. Therefore, plans of expansion in the new routes will be planned in advance according to current standards. Disposal. Once the end of the system lifetime has been determined, the system will be dismantled and disposed accordingly to guidelines and regulations. During the retirement, the system will be broken down into 4 subsystems to be decomposed. The first subsystem will be the magnetic railway system. Due to the rail system being embedded in the city streets, UTEP will relinquish ownership of it to the city of El Paso and TxDOT. The shuttle buses will have the AI system sensors, and any added equipment will be stripped. The remaining original manual operated shuttle bus will then be taken into UTEP's surplus inventory for resale. The UTEP technical support will be taken over by UTEP's facility maintenance team. The AI will be dismantled into hardware and software components. All hardware components will be salvaged, and if applicable, will be repurposed for other departments as within the UTEP facilities. A record of all software will be stored in local database for use in studies and as groundwork for future projects. Quality metric. For our project to be constructed, a quality metric table. This table would be consistent for the hours we spend for each phase of the project and the number of defects that were both ejected and removed from it. From these numbers, we were able to calculate the percentage of different items that were done during a specific phase. This allows us to see where and where not to spend time and what phase had the most defects on it. We were able to find out the table with the help of our defect log and assume similar values for the remaining phases. With all of our information recorded, we were able to calculate the cost of assessment, failure, and quality. To calculate the cost of assessment, we took a sum of the hours for the review phases we performed, which were 91 hours, and multiplied by 6, since we have 16 members. This number would be in our review cost, since we did not have any real cost for this project. Taking that review cost and dividing it by the total number of hours for the project, we would be given a cost of assessment. For our project, we calculated 76.7% as our cost of assessment. We were also able to calculate an assumed cost of failure for our project. Because we could not be constructing a physical model, we would have made certain assumptions to fill in the testing times. Then, we added together all the times for all of our testing phases and came up with our testing time. If we take our testing time and divide it by the total number of hours for our project, we would be given a cost of failure. For this project, we calculated the cost of failure to be 53.4%. Having both the cost of assessment and our cost of failure, we could now calculate our cost of quality for our entire project. By taking the cost of assessment and dividing it by the cost of failure, we would be given our cost of quality. Then we were able to calculate the cost of quality to be 1.44. This was acceptable for a project since the ideal cost of quality is 2. We could have improved our project by spending more time in certain review phases. Conclusion. This system will provide students and professors, faculty, with a more efficient way to move around campus. This system is also intended to innovate the current shuttle system in place, which wastes time and money, as it does unnecessary stops when the students are not around to be picked up, or paid drivers when the AI is proposed in our proposed system will be allowed the shuttle bus to maneuver on its own. The proposed system will not only benefit the students at UTEP, eventually the system can be used